bond length, and that bond length was the distance between different nuclei, and we showed the bond length is different depending on what the two atoms are that are close to each other. So we had different values for like hydrogen, hydrogen, and carbon, hydrogen. And so those bond lengths depend on various factors. So in general though, if the bond length is shorter, the bond strength is higher. So figuring out the bond length first, which is like this optimal lowest potential energy difference, and then what causes that difference. And then once you know the bond lengths, then you could say what the relative bond strengths are, and we're going to relate those down here. The bond dissociation energy is the amount of energy that has to go in to break one of those bonds, and that follows the trend that we have up here. So I just put some bonds down here and gave their bond dissociation energies and corresponding bond lengths so you could see that. So HF, so all of these have hydrogen on them. HF has, that one has the smallest atomic radius, if you remember, and then it increases as we go down the column. So it has the smallest atomic radius, which corresponds with its bond length. So as you go down, you can see that the bond length is getting longer. And as the bond length is getting longer, notice that it takes less energy to dissociate or break that bond. So like breaking these bonds as we go down requires less energy. So less energy to break the bond because those bonds, those atoms are farther apart from each other. And then the other thing I want to notice, or for you to notice because you just recently worked with thermodynamics, is it's an energy, and one of our energy units is like joules or kilojoules, so that's the energy to break these bonds. This one requires more energy because it's a higher number to break that bond.